All right, welcome to Tollefson Physics. So what today we're going to do is we're going to look at an object, in this case a sled, going down an icy hill. But there's a little bit of friction. So the coefficient of friction is going to be really low. And what we're going to do is we're going to predict the acceleration of this sledder. All right, so let's take a look at the problem that I'm talking about. Is we've got this sledder, and we're going to say that the hill is 30 degrees above horizontal, and that the coefficient of friction is 0.05. And that might feel like there's not enough information for this problem, but believe you me, this is actually enough for us to figure out what the acceleration of this sledder is going to be. Okay, so let's do that. So we're going to start with a force diagram in this particular case. So a force diagram I'm going to draw down here. I've got the force due to gravity pointing down towards the middle of the earth. Then if I kind of there's the hill. So the normal force, normal means perpendicular. So just to emphasize that, perpendicular to the hill surface. So I have a normal force, and then I'm going to have this tiny little force of friction. Hopefully it's not too big because we want to go down the hill quite quickly, don't we? All right, so now let's think about how to handle that. So this is the way you draw the force diagram if asked for it on the AP test. But to be able to solve this, I'm going to break this up into components. And this you'd have to do in a different place on the test typically. But what I'm going to do is, well, let me actually do my coordinate system first. So my XY coordinate system matches the hill. Why? Because it's going to, I know it's going to accelerate on the hill. And so I need one of my coordinates to be downhill. Otherwise the problem mathematically is a pain. Don't do that to yourself. All right, and so then I'm drawing one, so I'm breaking this one FG arrow up into two that follow this coordinate system. So here's the Y component, so that's FGY. And then here's the X component, parallel to the hill, right? That's my right angle, FGX. Right? I'm trying to get all my arrows in either in the X direction or the Y direction because then it becomes much simpler. And then I can write equations based on my force diagram now. And so let's go ahead and we know that it's not accelerating off the hill in the Y direction. So I can write the normal force equals the force due to gravity in the Y direction. So if I think about that, I don't have a lot of room here, but the 30-degree angle is up here. And this is next to it. And so what I would get is the force due to gravity is calculated as mass times the acceleration of gravity. And then that's the cosine. In this case, it's 30 degrees, but I'll just write theta because it's faster. Now, it's accelerating in the other direction. So I got to deal with that acceleration in that direction. And so I'm going to start, I'll start with F net equals ma, so one version of Newton's second law. And so I'm going to rewrite F net. I'll write it right here. And so what's going downhill, that's the direction it accelerates. It's FG in the X direction. What's going uphill, that is FF in the other direction. All right, so that's what my equation looks like. I'm going to simplify that a little bit. And so I'm going to have mass times acceleration. So how do we do FG? Well, it's mass times gravity, and then the X component is sine of the 30-degree angle. Right? So let me just emphasize, I'm using the theta as 30 degrees. And that's going to equal, well, what's another way to say force of friction? It's to say coefficient of friction times the normal force. So that's another way that we can say force of friction. Okay, well, what's the normal force? Well, actually, we have it listed right up here. Fn equals mg cosine theta. So let's substitute that. Ma equals mg sine theta minus coefficient of friction, and then the normal force, which is mg cosine theta. And then this does kind of a magical thing, right? So it has mass in every single term. Mass here, and mass here. So it's in all my terms, so I can divide out mass. Mass doesn't matter. Doesn't matter if this is a toddler or a full-grown adult. It doesn't actually matter if it's a bus that's on the same kind of sled that has this coefficient of friction. It doesn't matter. It just doesn't matter. All right, so then I get acceleration equals g, and I'm going to actually put g together, sine theta minus coefficient of friction cosine theta. So I just simplified that a little bit. So then it's a matter of substituting in numbers. Let's do meters per second squared. And then sine of 30 degrees is 1/2. Well, I'll just write it this way. So sine 30 degrees minus 0.05 cosine 30 degrees. Make sure your calculator is not in radians mode. So sine, like I said, sine 30 is 1/2. And my calculator is in radians mode because it gave a really strange number. That's how you know. Okay, so sine 30 degrees is 1/2, and then 0.05 times cosine 30 degrees is 0.04. And so this term right here gives me 0.456. Multiply that by 10. And so the acceleration I get, and I'm going to round it, is 4.57 meters per second squared. All right. So this is where it gets to be important to, you want to write things out. So if you don't see a path forward and you see something where they don't give you a mass and they're asking you to solve something, you're going to be able to solve it. And so if you don't see the way to solve it, what you want to do, in a problem like this, start with a force diagram. Try to write out what's happening in the x direction. Try to write out what's happening in the y direction and see where it takes you. Because once you write those out, it actually starts to show itself what you can do with it. You can see the fact that mass in this particular case canceled out, and then you can solve for a numerical value. So the acceleration is almost half of the acceleration due to the Earth's gravity in this particular case, right? So once we know that, if we knew the distance they were traveling, we could predict how fast they're going at the bottom of the hill or something like that using our kinematic equations. So problem-solving technique is just take it step by step. Even if you don't know where it's going to go, it's probably going to lead somewhere that's going to be helpful. So that's an example with hill and friction all together. So you need to work these kind of examples to really be able to understand them. And you can always find examples like this on the internet or in your textbook, and I really encourage you to follow up on those and try to solve them on your own.